This set of notes continues to look at maximum likelihood estimation relative to logistic regression models. We are going to further look at how to find maximum likelihood estimates and also some information that results from doing maximum likelihood estimation. The first thing that we're going to examine is something called a variance-covariance matrix. Now, we've seen a matrix-like structure with inside of R before, but we haven't necessarily looked at matrices in a mathematical context. So just to give you a brief introduction to this, let's answer the question of, well, what is the matrix, or what is a matrix? A matrix simply is a number of elements that are assembled into rows and columns. So in this particular case here, we have 2 rows and 3 columns of numbers. This 1 here is often referred to as the 1, 1 element. The 6 here will be referred to as a 2, 3 element, where we always say the row number first and the column number second. Now, one can do arithmetic, one can do algebra with matrices, just like what you would learn in a, let's say, a regular old algebra class, but now one can do it in a matrix-like format. If you want to have like an introduction to that, you can see my multivariate course notes available from chrisbiller.com, and also my linear regression course notes as well. In our particular class, we will at times see these mathematical matrices. However, you're never going to need to know how to necessarily add matrices together, multiply matrices together, or maybe even invert matrices. But unfortunately, we just can't get around totally not seeing matrices altogether. So what you need to get out of it, if you're not familiar with matrix algebra, is you need to be able to understand the basic construct of what a matrix is, as I just described. Fortunately, R will be able to handle our matrix algebra calculations for us. So with that as a very brief introduction, we're going to be talking about something called a variance-covariance matrix for our estimated regression parameters that results from our doing maximum likelihood estimation. And so here is what the variance-covariance matrix looks like. In this particular case, there are going to be p plus 1 columns. So this dot, dot, dot just allows me to not put column 3, column 4, and so on. There are going to be p plus 1 rows. And in each cell of that matrix, or element of each matrix, is something that's very important to us. In particular, the 1, 1 cell is the estimated variance of beta hat 0. The 2, 2 cell is the estimated variance of beta hat 1. And then we can keep on going to the p plus 1 and p plus 1 cell. This is the estimated variance for beta hat sub p plus 1. These variances are found in a very similar manner to what we saw previously when we were dealing with maximum likelihood estimators, when we only had one to worry about. If you remember, we had to work with, for example, a second derivative of a log likelihood function, find an expected value of it, invert it, and so on. And essentially, that's how these estimated variances come about. These elements, or these elements of a matrix that have equal row number, have an equal row number and equal column number, often referred to as the diagonal of the matrix. On the off diagonal of the matrix, we have these things that are denoted symbolically by a cove with a hat on top of it. What this represents is the estimated covariance of, in this particular case, beta hat 0 and beta hat 1. The estimated covariance of beta hat 0 and beta hat sub p. And if you haven't seen a covariance before, basically what it measures is the dependence between two random variables. In this case, we have two statistics. It measures the dependence much like a correlation coefficient. In fact, in an intro stat course where you first learned about correlation coefficients, this estimated covariance is essentially in the numerator of the equation that you would typically have represented in that kind of a course for the correlation coefficient. So it measures dependence. positive values, meaning positive dependence, negative values, meaning negative dependence, 0 means no dependence. Something that's interesting with this matrix has what's referred to as a symmetric structure. So notice that row 1 in column 2 is exactly the same as row 2 in column 1. That's what we mean by symmetric structure. So this is the estimated variance covariance matrix associated with our estimated regression parameters. It summarizes information about variability and dependence amongst our estimated regression parameters. We will be using this a lot throughout our course. And I'll give you one small place shortly. So as I brought up just a few minutes ago, when we've dealt with maximal likelihood estimators before, we had this nice expression for the estimated variance for a maximum likelihood estimator. We can now extend this from just one MLE to now P plus 1 MLEs, beta hat 0 through beta hat sub P, and this leads then to a matrix-like structure. So if I have just, let's say, two regression parameters, beta 0 and beta 1, the estimated variance covariance matrix of these maximal likelihood estimators will be found like this. Again, notice I'm taking the second derivative with respect to the log likelihood function, but also I'm taking these partial derivatives, beta 0 and beta 1, with respect to it as well. Then what one can do is find then the expected value of each of these cells of the corresponding matrix, invert the matrix, wherever you then, in the result, wherever you see a beta 0, replace it with a beta hat 0. Wherever you see a beta 1, replace it with a beta hat 1. This is the matrix. Two notes, something I want to go back to that I failed to mention before, is just to make, instead of always saying variance covariance matrix, some people will just refer to this as a variance matrix. I will refer to it as a covariance matrix throughout the rest of my notes and in my book. Now, for those of you who do have a good matrix algebra background, what one could do is actually show that this formulation of the matrix has, of the variance covariance matrix, has a particular simplification. In particular, if I have a matrix, we'll call it X. Often people will refer to this as a design matrix, where this matrix has a leading column of 1s, and my explanatory variable values for each observation written down in the columns. So x sub 2, 1 represents for observation 2 its value for variable 1. That's my X matrix. If I transpose it, take it times a diagonal matrix that has pi hat times 1 minus pi hat on the diagonal for each observation, take it times the X matrix again and invert the matrix, you will get then this variance covariance matrix. In other words, you will get what's up there if you only had one explanatory variable. If you haven't had a matrix algebra class, that's fine. Don't worry about this representation here. I like to bring this up because there's students and readers of my book with a variety of different backgrounds, and so presenting something like this can help draw connections between what we're doing here with their background in another setting. So for example, if you've seen weighted least squares estimation fully represented in like a regression course, remember how that plays a role in the iteratively re-weighted least squares method to estimate these parameter estimates. If you've seen weighted least squares estimates before, this is the covariance matrix that you would have in a weighted least squares setting. Okay, enough about that. Let's get to an example to show you how in R you can have R automatically do these calculations for you. We're going to focus in the place kicking data on a model that has distance only as the explanatory variable. To calculate then the estimated covariance matrix, we can use a function called vcov, standing for variance covariance. Note that vcov is actually a generic function in R. And if I say vcov mod.fit, what ends up happening is I get a 2 by 2 matrix. So this is my estimated variance of beta hat 0. This is my estimated covariance matrix. I'm sorry, estimated covariance for beta hat 0 and beta hat 1. This is my estimated variance for beta hat 1. Because of the symmetry property of the matrix, notice how these two elements, even though they're written slightly different, are actually exactly the same. If I wanted to, I could extract a certain element from that matrix by putting the row number and the column number, putting it into brackets. Okay, now let's relate this to what we had gotten previously from the summary mod.fit output that we saw previously. In particular, I want to look at this column here called std.error. This stands for standard error. Explain that more in a second. And what we see here for the distance row, this is the square root of the estimated variance of beta hat 1. So if I were to square 0.008339, I will get 6.95 times 10 to the negative fifth power. Try that on your own to show that indeed that's what you get. A similar thing here. Here's the square root of the estimated variance of beta hat 0. So why is this column then called std.error? Well, in another stat course, you may have heard of this phrase before, standard error. All that standard error is just another name for the square root of the estimated variance of a particular statistic. That's it. And so that's how R labels it here. For those of you who have that matrix algebra background, if you want to see how you can calculate the estimated covariance matrix using matrix algebra, here is an example in my notes. Again, though, students are not expected to be able to do this on a test or any other kind of graded activity in our class. So the second main topic in this set of notes I want to talk about is that, let's say instead of having our data that we're trying to use GLM with, the GLM function with, suppose that instead of it coming in a Bernoulli response format where y is equal to 0 or 1, suppose instead it comes in a binomial response format. Let's say we have W, where W represents the number of successes out of a certain number of trials. How can we actually then estimate the corresponding regression parameters? And will these corresponding regression parameters for essentially the same data set but just rearrange will result in the same values? In the end, it will result in the same maximal likelihood estimates. So let's say now we have W1, which represents the number of successes for observation 1 out of N1 trials. And we have this all the way up to W sub capital J, which says for the jth observation, what's the number of successes out of N sub capital J trials. I use this J subscript here rather than saying I have N observations, just to help us differentiate the Bernoulli response format data from the binomial response format data. My likelihood function looks like this. Exactly the same as before, but now I have a binomial distribution with it. And notice we have that N sub j choose W sub j in there. I can find my log likelihood function as well. And so this looks very similar to what we had before. The main difference is this part right there that I circled. Now, to find the maximum likelihood estimates for the regression parameters, remember that this pi sub j would be something like, exp beta 0 plus beta 1 times x1j plus however many explanatory variables you have. Then you have 1 plus exp, and you write a similar thing there. Now, to find the maximum likelihood estimates of these regression parameters, I would just maximize this expression just like what we saw before with the Bernoulli response format. And you might be wondering, because I have this extra part here, will that change things? In the end, it does not. The reason is simply, notice you do not have any regression parameters written in there. And so in the end, for whatever the betas are, this part of the equation does not change. And so you're left with dealing with this right here. And if you wanted to, you could just rewrite these WJs as Ys, ones and zeros, and then start adding up the corresponding elements. And you can see that you're going to get into the same spot as you would have with Bernoulli response format data. So how can we do then the maximum likelihood estimation though in R? There are some small changes to the GLM function. Please pay special attention to them. This is a place that sometimes students in my classes miss, especially on tests. Okay, so we're going to go back to using the place-kicking data set, and I'm going to transform my data from a Bernoulli response format to a binomial response format where I have distance as the only explanatory variable. So in the end, this is what I want my data to look like, and I'll explain how I get this shortly. At a distance of 18 yards, there were a total of 3 trials. That would be like our n sub j, or in this case would be n sub 1. There were 2 successes at a distance of 18 yards, so that would be my W1. And if I were to take 2 divided by 3, I get my, let's say, observed number of successes at a distance of 18 yards, and that would be 0.67, 2 divided by 3. At a distance of 19 yards, I had 7 successes, so that would be W2. I have 7 trials, that would be my N2, so there was 7 kicks at 19 yards, and so I observed all successes, so my estimated proportion of successes was 1. At 20 yards, notice I had 776 successes out of 789 trials, so estimated proportion of about 0.98. Why did I have so many trials at that distance compared to everything else that you see there? Simply because for the rules of the NFL at that time, most PATs were attempted at 20 yards. There could be PATs at other distances, but most were at 20 yards. So that's why there's so many there. So how do I get the data in this format? Let me jump on over here to 10. And let me find the corresponding place in my code. There we go. So what I need to do is sum up all the successes, all the ones, you could say, we'll sum up all the ones and zeros that are for my good variable. That will give me my number of successes by a distance. And the best function to do this in R is a function called aggregate. So I'm going to aggregate my good variable by distance. And notice we have a syntax that looks somewhat similar to what we saw for the formula argument. Instead, we put this into an argument called x. My data is in place kick. And how do I want to summarize the good variable? I want to summarize by summing the values of good for each unique distance. And so if I put the results into W, we can see what we get. And there we have all the distances and the number of successes at each distance that we had just saw. Now to find the number of trials, I can do exactly the same thing, but I'm going to use a different summary function, fun standing for function, and it's going to be length. Length is just going to count for me the number of observations per unique distance. And so there's n. So 3 trials at 18 yards. And then I'm going to put this all together in a nice data frame where what I do is I create a variable called distance. I just simply extract the distances that were in my W data frame that I just created. I'm going to extract the number of successes from the good column of W. I'm going to extract the number of trials from the good column of N. And then I'm going to find simply the observed proportion of successes at each unique distance and round it to 4 decimal places. So if I run that code and look at the first 6 values using the head function, this is what I was showing you in the notes previously. Excuse me. So given this format of the data, how can I estimate the model? Well, I can use the GLM function once again. I'm going to put the results from using GLM into an object called mod.fit.bin, for the lack of a better name. And what I have highlighted here in yellow represent the main differences from what we've done before. I say formula equal. This is where I need to put in essentially my W variable. And then I say /n. So it's like I'm taking W divided by n. Number of successes for each unique distance divided by the number of trials. This isn't actually doing a division there, it's just more of a syntax so that you can see what's going on. Tilde, I put in my explanatory variable of interest. And then I need to say weight equal trials. What that tells R is, well, how many trials are there for each unique distance value? You might think that R could just figure that out by seeing this right there, but unfortunately it does not work out with this particular function in this syntax. Family argument's the same as before. My data now is in w.n, and here's my output. Here's my beta hat 0, there's my beta hat 1, here's my square root of the estimated variance of beta hat 1, and so on. And so what we can see here is the estimated logistic regression model is the same as what we saw before. Now there are other small parts of this output which will not be the same for where you have a Bernoulli format or a binomial format to your data, and that's okay. We will actually talk about that more later in the course for how we can use that information. Now, one last thing that I want to mention is that all the 2x2 contingency tables that we saw back in chapter 1, we could actually estimate a logistic regression model for those as well. So think back to the Larry Bird data set. I could create an explanatory variable called x. X is equal to 1 if, let's say, the first free throw was made. It's equal to 0 if the first free throw, I can't write, first free throw is missed. Okay. Then I can form my response variable. Let's let it be W here. W is equal to the number of successes for the second free throw attempt, depending upon if it's made or it's missed. You could form a data frame that has the corresponding bird data in it and estimate a logistic regression model on your own. That's something that I strongly recommend that you try to do. And if you have problems with it, please let me know, and I'd be happy to go over it during a class. So that concludes then this additional part of our notes that talks about parameter estimation for a logistic regression model.